How crowded is our cosmic backyard? Really? If intelligent life exists near us, where, exactly, could it be living? Not in some distant galaxy, but on specific planets within just 40 light-years of the Sun. How many real candidates do we actually have in that tiny slice of the universe, and which ones would you bet on? We tend to picture space as mostly empty, a few bright stars, a lot of black, and our lonely solar system drifting through the void. But while that picture feels right on a dark night, it falls apart the moment we start counting exoplanets, because inside a sphere just 40 light-years across, our quiet patch of the galaxy turns into a surprisingly crowded neighborhood, not with stars, but with worlds. In the hunt for alien life, this local bubble is our natural testing ground. It's close enough that we can actually measure things that matter for habitability, the size of a planet, the shape of its orbit, the heat from its star, even hints of an atmosphere. This means that for dozens of nearby systems, we are no longer guessing in the dark. We have data. We can start asking very specific questions. Could liquid water exist here? Could a stable climate form there? Would any of these places feel even remotely Earth-like? And the cast of characters is already remarkable. We have Proxima Centauri b, our nearest known exoplanet, circling a restless red dwarf just over 4 light-years away. We have the famous TRAPPIST-1 system, about 40 light-years out, with 7 tightly packed, Earth-sized planets sharing a fragile Goldilocks zone. We have LHS 1140b, a dense super-Earth that might, under the right conditions, hold on to oceans. We have GJ 1214b, a puffier world that could be wrapped in thick clouds, or even a steam-rich atmosphere. It should be noted that these are just a few of the confirmed worlds in range. Then there are the older, quieter systems, 55 Cancri, with its eclectic family of planets, from a scorching inner world to more temperate outer companions. Tau Ceti, a sun-like star long featured in science fiction, now known to host its own set of planets that may skirt the edges of the habitable zone. Optimistically speaking, if intelligent life has arisen nearby, it almost certainly lives on one of the planets we are about to visit. So, let's begin. So it's time to find out the truth about our cosmic backyard. By the end of this video, we will have visited every currently confirmed exoplanet within 40 light-years, and once we have seen them all, from blistering lava worlds to the few that might cradle oceans and atmospheres, you will be able to decide for yourself which one deserves your vote for life. Why nearby exoplanets matter more than distant marvels. When we talk about alien worlds, our minds often jump to distant, exotic systems thousands of light-years away. But in the hunt for alien life, the planets that matter most right now are much, much closer. There is a simple reason for that. Our telescopes, even the James Webb Space Telescope, are still limited by light. The farther away a planet is, the dimmer it appears, and the harder it becomes to separate its faint glow from the glare of its star. This means that planets within about 40 light-years are the ones we can realistically probe in detail, measure their sizes and masses precisely, tease out their atmospheres, and begin serious searches for biosignatures. It should be noted that exoplanet astronomy has exploded since the 1990s. From the first hot Jupiters to the thousands of worlds cataloged by Kepler and TESS, we now know that planets are everywhere. But while that catalog is huge, most of those planets are hundreds or thousands of light-years away. They are tiny shadows on distant stars, great for statistics, terrible for follow-up. By contrast, a world like TRAPPIST-1 or Proxima Centauri b sits close enough that JUICE and future telescopes can repeatedly stare, collect high-quality data, and actually characterize what is going on at the surface and in the atmosphere. So our 40 light-year bubble is not arbitrary. It is our immediate, cosmic neighborhood, the region where individual planets stop being anonymous dots in a database and start becoming places. If we ever manage to send an interstellar probe, perhaps a laser-driven sail, or some other future technology, it will almost certainly head to a star within this range. And if a radio signal or laser pulse from another civilization ever washes over Earth, odds are high it will have crossed no more than a few dozen light-years of space. That is why these nearby systems carry such enormous weight. The mix of worlds around our local red dwarfs and sun-like stars will shape our answer to a profound question. Is Earth rare, or is it typical? If our neighborhood is full of small, rocky, habitable planets with thick atmospheres, we might conclude that life is a common outcome of planet formation. If instead we find mostly scorched rocks, frozen deserts, and mini-Neptunes, then, optimistically speaking, complex life could still exist elsewhere, but it may be far more scattered than we hoped. So it's time to find out the truth in a more practical sense. How do we even detect and confirm small, dim planets around faint red dwarfs and relatively bright sun-like stars within this 40 light-year sphere? How many worlds have survived the scrutiny of multiple telescopes, and what kinds of systems have we uncovered so far? The answers are stranger and closer to home than you might expect. From empty sky to planet census, how we count our neighbors to turn that abstract question into something we can actually work with, astronomers do something very simple but very powerful. They keep a census. Within 10 light years, within 20, within 40, teams around the world maintain living catalogs of every confirmed planet we have solid data for. Each entry is a kind of cosmic ID card, which star it orbits, how far away that system is, how massive the planet is, how big it is, and whether it might be even slightly habitable. In the hunt for alien life, this is our neighborhood phone book. But how do we fill in that phone book when the planets themselves are almost always invisible? We rely on two main tricks. The first is radial velocity, where we watch the star itself. As a planet orbits, its gravity makes the star wobble very slightly toward and away from us. That motion imprints a tiny rhythmic shift in the star's spectrum. From that, we can weigh the planet, at least get a minimum mass, and estimate its orbit. The second method is transit photometry. Here, instead of watching the star's motion, we watch its light. If the orbit is lined up just right, the planet crosses the face of the star from our point of view, causing a small, periodic dip in brightness. The deeper the dip, the larger the planet's radius. This means that, with transits, we can measure size directly. Now here's where our local census really becomes powerful. Nearby systems are often discovered first by radial velocity, especially around bright sun like stars and some red dwarfs. Then, if geometry is on our side, we later catch those same planets in transit. Suddenly, we have both mass and radius. Divide one by the volume implied by the other, and we get density. Rocky Earth, like world, puffy mini Neptune with a thick atmosphere, dense iron-rich remnant, the numbers tell us. Pattern interrupt for your brain. Within 40 light years, there are almost certainly hundreds, maybe thousands of planets. We have only confirmed several dozen. It should be noted that this mismatch is not because the planets are rare, but because our methods are biased. Radial velocity is best at finding big planets close to their star. Transits favor systems whose orbits just happen to be edge-on from Earth. Small, temperate worlds in the Goldilocks zone are the hardest to detect, even though they may be the most interesting for life. Optimistically speaking, our 40 light-year catalog is just the tip of the iceberg. So, let's begin our tour of the part we can already see. For each system, we will look at the type of star, its distance, how many planets it hosts, and what we know about each world's orbit, size, and potential habitability. And of course, we have to start with the very closest star system to the Sun. Meet the nearest neighbor, Proxima Centauri's troubled world. So, if we want to understand our cosmic neighborhood, we have to ask a very direct question. What is really happening around the closest star beyond the Sun? Because the first stop on our tour is not just nearby, it is practically next door. Proxima Centauri sits only about 4.24 light-years away, a tiny red dwarf loosely orbiting the brighter Alpha Centauri A and B. It should be noted that this makes Proxima the closest individual star to us, and that proximity is pure gold for planet hunters. The closer the star, the easier it is to measure the tiny gravitational wobble it feels from an orbiting planet. This is why Proxima became a prime target for radial velocity surveys long before we knew it hosted a world. In 2016, the data finally revealed that world, Proxima Centauri b. On paper, it sounds almost comfortingly familiar. The planet has a minimum mass close to Earth's, and it orbits so tightly that a year lasts only about 11 days. That is far inside Mercury's orbit in our own system. Yet Proxima is so dim that Proxima b still receives roughly similar energy to Earth from the Sun. This means, at least in terms of raw starlight, it sits in the famous Goldilocks zone. In the hunt for alien life, that phrase is irresistible. A nearby, roughly Earth mass planet in the habitable zone of the closest star in the universe we can visit beyond our own, it sounds almost too perfect. But while the orbit looks promising, the star itself tells a more violent story. Proxima Centauri is a flare star, unleashing bursts of high-energy radiation that can outshine its normal output for minutes to hours. These flares can strip atmospheres, break apart water molecules, and bathe the planet in X-rays and ultraviolet light. So it's time to find out the truth. Is Proxima b a gentle, ocean-bearing world, or a sterilized rock scorched by constant stellar tantrums? At such a close orbit, tidal forces are extreme. Over time, they almost certainly slowed the planet's rotation, until one hemisphere now permanently faces the star, while the other faces endless night. Imagine a world with a blazing dayside, a frozen nightside, and perhaps a narrow twilight ring, where temperatures might be more moderate. If an atmosphere survived, winds could redistribute heat and create strange climate patterns that do not resemble Earth at all. Optimistically speaking, that thin ring of eternal sunset could still be habitable, but without a robust atmosphere, Proxima b might simply be airless, its surface locked between radiation and deep freeze. Upcoming observations with JEST and future missions will not easily take a direct image, but they can look for subtle signatures, hints of an atmosphere, temperature contrasts, maybe even clouds. So, let's begin with this tension. Is our nearest exoplanet our best hope for nearby life, or our clearest warning that red dwarf systems may be more hostile than they first appear? Alpha Centauri's other secrets, planets we might have missed, so if Proxima b might be more warning than welcome, what about the rest of our nearest stellar neighbors? In the hunt for alien life, there is one system that refuses to stay out of the spotlight: Alpha Centauri. Two bright sun-like stars, A and B, just 4.37 light-years away, practically next door on the scale of the Milky Way. We know that Earth-like planets are fertile ground for life. After all, life arose here. So when we see a pair of stars that look broadly similar to our own sun, our instincts say, this is where we should search first. But while that sounds simple, the reality is much more complicated. Alpha Centauri A and B are locked in a tight binary orbit, swinging around each other every 80 years or so. Each star's gravity constantly tugs on the other, shifting their spectra and their apparent motions on the sky. For planet hunters trying to measure the tiny wobble caused by an Earth mass planet, this is a nightmare. The stars are also very bright, which is wonderful for gathering data, but terrible if you want to see the faint reflected light of a small planet lost in the glare. So, let's begin with a hard truth. It should be noted that as of right now, there are no universally accepted, confirmed exoplanets around Alpha Centauri A or B in the official catalogs. Over the past decade, teams have reported tantalizing signals, hints of a roughly Earth-mass planet around Alpha Centauri b, whispers of something in a short orbit around A, even a possible warm world seen in thermal imaging. But while some of these candidates briefly made headlines, none has survived detailed reanalysis without serious doubts. Why is that? Because our instruments are just at the threshold of what we need. The wobble of a true Earth analog around a sun-like star is smaller than walking speed. Stellar activity, spots, flares, convective cells can mimic that signal almost perfectly. This means that even for the very closest sun-like stars, we are still arguing over whether we are seeing planets or just the stars themselves breathing. Optimistically speaking, this is exactly why Alpha Centauri has become a design target. New extreme precision spectrographs are being built to reach down to just a few centimeters per second in radial velocity. Direct imaging projects, including concepts for tiny star shades or interferometers, are being planned with Alpha Centauri A and B as their first light targets. If we confirm even one small planet in the Goldilocks zone there, it would instantly become a top priority for atmosphere studies, and, eventually, for interstellar probe concepts. So it's time to find out the truth on a larger scale. If our very nearest sun-like stars still look blank in the confirmed planet lists, what does that say about the rest of our 40 light-year neighborhood? Are we seeing the real landscape, or just the brightest peaks of a much larger planetary iceberg waiting in the dark? A quick detour. How many worlds hide within 40 light-years? To see that iceberg, we need to zoom out and count. How many alien worlds have we actually confirmed within 40 light-years of the Sun? The answer, right now, is only a few dozen confirmed exoplanets. Depending on the catalog you check, we are talking on the order of 40 to 50 worlds. It should be noted that this tally is always shifting as new planets are announced, old candidates are rejected, and orbits are refined. In the hunt for alien life, even a single promotion, from maybe to confirmed, can change how we think about our neighborhood. But while that raw number sounds modest, the pattern behind it is dramatic. Most of these planets do not orbit Sun-like stars at all. They circle small, cool red dwarfs, systems like TRAPPIST-1, Proxima Centauri, LH1140, GJ1214, GJ367, and several more with less famous names. Our local bubble of the universe is overwhelmingly ruled by these tiny stars, and our exoplanet census reflects that reality. Around true solar analogs inside 40 light-years, we have surprisingly few confirmed planets. This means that when we talk about nearby exoplanets, we are mostly talking about worlds huddled close to dim red embers, not sprawling systems like our own. Their Goldilocks zones are pulled inward, their years are measured in days, and many planets are likely tidally locked, with one face in eternal day and the other in endless night. Already, that reshapes our expectations for what a habitable planet might look like. If we sort these nearby planets by size, another pattern jumps out. The majority are roughly Earth-sized, or super-Earths, up to a few times our planet's mass and radius. TRAPPIST-1 alone gives us 7 examples. Add Proxima b, LHS 1140b, GJ 367b, and several others, and suddenly compact rocky or ice-rich worlds dominate the list. Mini-Neptunes and gas giants certainly exist within 40 light-years. 55 Concrete E and GJ 1214b are prime examples, but they are outnumbered by these smaller, denser planets, where a solid or ocean surface is at least plausible. Here is the quiet twist. A big fraction of our total count comes from just a handful of multi-planet systems. TRAPPIST-1 contributes 7. 55 Concrete adds at least 5. Tau Ceti offers several candidates and a few confirmed worlds, packed into tight inner orbits. With only a few stellar names, we suddenly account for a large slice of every known planet in this volume of space. So, let's begin connecting the dots. Our nearby exoplanet landscape is built on red dwarfs, rocky worlds, and compact multi-planet systems. Optimistically speaking, that is exactly the kind of architecture where life might find many different footholds. But before we dive into TRAPPIST-1 and its 7 Earth-sized worlds, we need to understand why these problematic little red dwarfs keep stealing the spotlight in the search for life, and why we keep pointing our best telescopes back at them. So it's time to find out the truth about the stars themselves. Red dwarfs, tiny stars, huge influence on nearby planets. So, if these stars are so problematic, why do they completely dominate our nearby exoplanet map? In the hunt for alien life, that is the uncomfortable question we keep running into as we scan the space within 40 light-years of the Sun. Red dwarfs, or M-dwarfs, are tiny by stellar standards. Our Sun is a bright yellow furnace. A typical red dwarf is smaller than half its size, much cooler, and so faint that, viewed from interstellar space, it would barely glow ember red. Yet this is the cosmic plot twist: they are by far the most common kind of star in the Milky Way. It should be noted that in our local neighborhood, roughly 50 of the closest 60 stars are red dwarfs, including Proxima Centauri itself. This means that when we look for planets close to home, we almost cannot avoid them. Statistically, most of the stars inside 40 light-years are these dim little objects, so most of the planets we discover end up circling red dwarfs rather than sun-like stars. And strangely, that is good news for planet hunters. Why? Because red dwarfs make the planets easier to see. A small, low-mass star wobbles more dramatically when a planet tugs on it, so the radial velocity signal stands out more clearly in the data. At the same time, their tiny size means that an Earth-sized planet crossing in front blocks a much larger fraction of starlight. A transit that would dim a sun-like star by a whisper can dim a red dwarf by a noticeable blink. So, let's begin to appreciate just how powerful that is. Proxima b, TRAPPIST-1's 7 worlds, LHS 1140b, GJ 367b, and several others we will meet are all beneficiaries of this effect. Without these small stars, many of those Earth-like or super-Earth planets would be invisible to us today. Optimistically speaking, red dwarfs might be handing us a shortcut to studying potentially habitable atmospheres decades earlier than we expected. But while red dwarfs help us find planets, they also stack the deck against life. Their Goldilocks zones sit huddled very close to the star, where a planet must orbit in just a few days to receive the right amount of energy. At those distances, tidal forces tend to lock one side of the planet permanently into day and the other into endless night. Can a stable global atmosphere really move heat around fast enough to keep such a world habitable? On top of that, many red dwarfs unleash powerful stellar flares, intense X-rays, and fast particle winds. Over hundreds of millions of years, those outbursts can erode an atmosphere, boil away oceans, and sterilize surfaces. Proxima b lives under that kind of assault. TRAPPIST-1 is calmer, but still no gentle sun. LHS 1140b might be thickly cloaked or stripped bare. Right now, the evidence is finely balanced, so we are left with a central tension. Are planets around red dwarfs our best chance to detect nearby life precisely because they are so easy to study, or are we mostly staring at beautifully aligned dead rocks while the real action hides around rarer sun like stars farther away? In the next systems, we will watch this trade-off play out in detail. TRAPPIST-1, the compact 7-planet showstopper to answer that tension. We do not have to look far, we just have to look toward one of the most famous red dwarf systems in the entire sky. So, let's begin with the compact showstopper, TRAPPIST-1. This star sits right near our 40 light-year boundary in Aquarius, and yet its entire planetary system would fit comfortably inside the orbit of Mercury. 7 known planets, all roughly Earth-sized, all lined up in an extraordinarily tight configuration. In the hunt for alien life, this is the poster child for if not here, then where. TRAPPIST-1 itself is an ultra-cool red dwarf, only about 9% the mass of the Sun, and slightly larger than Jupiter in radius, but far more massive than any planet. Its surface temperature is less than half the Sun's, and its luminosity is only a tiny fraction of our stars. This means its Goldilocks zone is squeezed right up against it. To get Earth-like warmth, a planet has to orbit in just a few days instead of a full year. That is exactly what these 7 worlds do. Every single one transits, passing in front of the star from our line of sight, causing tiny dips in brightness that telescopes like Spitzer, Hubble, and now JWST can measure with exquisite precision. Because they all line up, we can time their orbits, weigh them using their mutual gravitational tugs, and search their atmospheres for even the faintest traces of gases. It should be noted that this combination is incredibly rare. Most systems do not give us this kind of perfect laboratory. The inner planets, B, C, and D, skim close to the star, while E, F, and G sit in or near the habitable zone, with H trailing farther out in the cold. But while that sounds chaotic, the orbits themselves are locked into a delicate resonant chain. Each planet's orbital period is in a near integer ratio with its neighbors, like gears in a cosmic clock. This means tiny changes in timing reveal their masses and densities, confirming that these are rocky, Earth-like planets, not puffy gas dwarfs. Optimistically speaking, such a calm, resonant configuration hints that the system may have formed gently, without violent scattering that would strip atmospheres or fling planets into the star. So it's time to find out the truth. Did that gentle history actually preserve air and water on any of these worlds, or did the harsh radiation of a young red dwarf erase their chances? JWST is now delivering the first serious verdicts on whether these planets have atmospheres at all, and the results are not just about TRAPPIST-1. This means the next few spectra will reshape how we think about red dwarf habitability across our entire 40 light-year neighborhood. Because if 7 nearly ideal targets cannot hold on to air, what does that imply for the rest of our nearby systems? How TRAPPIST-1 was found, from 3 planets to 7 so. If TRAPPIST-1 is now our stress test for red dwarf habitability, how did we even find this tiny star and its 7 Earth-sized planets in the first place? The answer does not start with JWST. It starts with a much smaller, almost modest project on the ground. In the hunt for alien life, most of the attention goes to giant space telescopes. But while those grab the headlines, the Teegarden Planets and Planetesimals Small Telescope, or TRAPPIST, quietly stared at the sky from Chile and Morocco. 2 60-centimeter telescopes, deliberately tuned to watch faint, cool red dwarfs, night after night, waiting for the slightest dip in starlight that might betray a passing planet. TRAPPIST-1 itself is so dim that, from Earth, it looks more like a failed ember than a classic star, yet that made it perfect. Because the star is small, an Earth-like planet blocks a relatively large fraction of its light. So, let's begin with the very first hint. In 2015, the team noticed repeated, shallow drops in brightness from this one unremarkable red dwarf. Not once, but over and over, with different timings. Those dips were the fingerprints of the first 3 planets, TRAPPIST, 1b, C, and D. Each time one of them crossed the face of the star, the light curve stepped down by less than 1%, then back up again. By tracking the pattern of those steps, astronomers could measure their orbits and sizes. It should be noted that this was already extraordinary, 3 roughly Earth-sized worlds around a single ultra-cool star, all within our 40 light-year neighborhood. Then came the pattern interrupt. What if there were more? The initial ground-based data hinted at extra, unexplained dips that did not quite fit the 3 known orbits. To sort signal from noise, astronomers turned to bigger telescopes on Earth, and, crucially, to NASA's Spitzer Space Telescope, which could stare continuously in the infrared for weeks. Spitzer extended the time baseline from months to hundreds of days. With that long, uninterrupted gaze, additional transit signals began to crystallize out of the noise. One, then another, then another. This means the simple 3-planet picture dissolved into a compact, resonant chain of 7 confirmed rocky planets, all packed closer to their star than Mercury is to the Sun, 3 of them in the Goldilocks zone. Optimistically speaking, TRAPPIST-1 became the prototype of a new kind of planetary system. It showed how patience, relentless monitoring, and careful analysis can transform a faint point of light into a detailed laboratory for studying atmospheres, climates, and orbital dynamics. So it's time to find out the truth lurking behind that success story. If one tiny red dwarf within 40 light-years can host 7 rocky planets, what fraction of our nearby red dwarfs might hide similar systems. And just beyond our current detection limits, how many TRAPPIST-1 analogs are quietly waiting for their first measured dip in starlight? TRAPPIST-1's inner infernos, planets B and C up close. So, if TRAPPIST-1 is our nearby success story, what happens when we zoom all the way in on its most extreme worlds? In the hunt for alien life, it is tempting to skip straight to the Goldilocks zone. But before we do that, we need to understand what the star does to the planets huddled closest to it. So, let's begin with TRAPPIST-1b and TRAPPIST-1c, the innermost members of this compact system. TRAPPIST-1b whips around its red dwarf in just about a day and a half, while TRAPPIST-1c takes roughly 2.5 days to complete an orbit. A year there is shorter than a weekend here. Both planets receive several times the energy that Earth gets from the Sun, bathing their surfaces in relentless stellar radiation. On paper, they look deceptively Earth-like. Each one is only slightly larger than our planet, with masses in the same general range. This means their surface gravities are not wildly different from Earth's, and their rocky compositions fit neatly into the terrestrial planet category. But while the numbers sound familiar, the environments do not. At these distances, any surface liquid water would be boiled away. Instead, we are likely dealing with scorched rock, possibly even global magma oceans on the daysides, glowing a dull red under the constant glare of the star. So it's time to find out the truth about their atmospheres. Early hopes imagined thick, Venus-like blankets of carbon dioxide, trapping heat and perhaps creating exotic weather. Dwes stepped in to test that idea by measuring how much infrared light these planets emit as they pass behind the star. If they had puffy mini-Neptune atmospheres, the thermal signatures would be very different. The data told a harsher story. TRAPPIST-1b, and likely TRAPPIST-1c as well, appear to lack those thick, extended atmospheres. Their thermal emission is closer to bare rock than to a world wrapped in deep gas. It should be noted that GIWEST can still allow for extremely thin envelopes, maybe trace carbon dioxide, or other molecules clinging to the surface, but nothing like the dense protective shields we once imagined. These planets may be nearly airless. Why does this matter for our broader 40 light-year survey? This means that close-in planets around red dwarf stars might systematically lose their atmospheres over time. Intense irradiation, high-energy particles, and flares can strip gas away, molecule by molecule. Optimistically speaking, that might clear out uninhabitable inner worlds and leave more stable conditions farther out. But while that sounds hopeful, it raises a chilling question. If TRAPPIST-1b and 1c are already scorched and stripped, what about the planets in the habitable zone? Can TRAPPIST-1d, E, and F hold on to their air under the same stellar temper tantrums, or is the entire system slowly being eroded by its own star? In other words, are we seeing a warning sign for red dwarf habitability right in our cosmic backyard? The temperate trio, TRAPPIST-1, E, F, and G in the spotlight, so if the inner worlds are stripped bare, what hope is left for the planets we actually care about? In the hunt for alien life, everything now hinges on the temperate middle of the TRAPPIST-1 system. So, let's begin with the trio that has captured so much attention, TRAPPIST-1e, F, and G. These are the middle planets, each sitting at a different sweet spot of stellar energy. TRAPPIST-1 receives a little less light than Earth, F is closer to what Mars gets, and G sits out near the dim edge, almost like a colder cousin of Mars. This means, on paper, they span the star's Goldilocks zone, where liquid water could exist on a rocky surface. But are they actually rocky? Current measurements say yes. TRAPPIST-1 is almost a twin of Earth in size and mass, with a density that strongly suggests an iron core and silicate mantle. TRAPPIST-1, F, and G are also close to Earth-sized, slightly less dense, but still consistent with compact, mostly rock and water compositions rather than puffy gas envelopes. It should be noted that for exoplanet scientists, this is already remarkable. 3 nearby planets, all roughly Earth-like in scale, all in or near the habitable zone of a single red dwarf star. Now the real question, do they have atmospheres? This is where the James Webb Space Telescope moves from impressive to absolutely essential. When these planets transit, a tiny fraction of starlight filters through any atmosphere they might have. By spreading that light into a spectrum, DREST can look for the fingerprints of gases, like carbon dioxide, water vapor, or even the telltale flatness that would mean no substantial air at all. For TRAPPIST-1, F, and G, teams are stacking many transits, squeezing every photon out of the data. Early results hint that thick, hydrogen-rich envelopes are unlikely, especially for E. That already rules out one major class of non-habitable, mini-Neptune-style worlds. But while that sounds promising, the spectra are subtle, noisy, and still under intense debate. Are we seeing thin, compact atmospheres, high-altitude clouds, or simply bare rock? So it's time to find out the truth about red dwarf habitability. The stakes could not be higher. If even one of these planets clearly shows a stable, substantial atmosphere after billions of years of early flares, it would be proof of concept that some red dwarf systems can nurture long-term, potentially habitable environments. Optimistically speaking, that would echo across our interpretation of dozens of nearby stars within 40 light-years. And if they are all airless, or steam-choked, or frozen out, then TRAPPIST-1 becomes a cautionary tale, a sign that Earth-like orbits around red dwarfs may not be enough. In the next section, we will see how astronomers are already using this fragile, incomplete verdict to rethink other nearby systems, and where we should look next. Outer siblings and system verdict, TRAPPIST-1d and H. So if TRAPPIST-1 is our headline act, what about its siblings just inside and far outside the Goldilocks zone? To understand this system as a whole, we need to look at how it brackets habitability from both sides. So let's begin with TRAPPIST-1d. This planet orbits close in, circling the red dwarf in just about 4 Earth days. It receives roughly 1.1 to 1.5 times the energy Earth gets from the Sun, depending on the model you use. That puts it right on the inner edge of the habitable zone, where a little extra starlight might push oceans toward a runaway greenhouse, but clever atmospheric circulation could still keep parts of the surface temperate. In terms of size and mass, TRAPPIST-1d is only slightly smaller and lighter than Earth. Surface gravity would feel familiar. This means that on paper it looks appealingly Earth-like, yet its orbit is so tight that one hemisphere always faces the star. The day side could be borderline hot, while the night side might be frigid, unless a thick, dynamic atmosphere or deep ocean moves heat around efficiently. On the other side of the system, we find TRAPPIST-1h, the outermost known planet. It takes about 8 days to orbit the star, and receives only a tiny fraction of Earth's sunlight, closer to what Pluto gets from our sun than what we enjoy here. It should be noted that around such a dim star, that still places it relatively nearby, in absolute distance, but in terms of energy, this world is almost certainly cold and dark. TRAPPIST-1h is also small and low mass, with gravity weaker than Mars. It is roughly Earth-sized in radius, but probably less dense. Optimistically speaking, if it held onto a very thick hydrogen-rich atmosphere, that envelope could trap heat and perhaps maintain pockets of liquid water under a global ice shell. More realistically, many models suggest a frozen, air-poor world, where volatiles have either escaped or are locked away as ice. Here is where Jebwist comes back in. In the hunt for alien life, we often celebrate atmospheric detections, but with TRAPPIST-1d and H, non-detections are just as important. So far, Webb has not clearly seen strong signatures of thick CO, water vapor, or methane in transmission. This means that if these planets have atmospheres, they are either relatively thin, unexpectedly clear, or dominated by molecules that are hard to detect with current data. Taken together, all 7 rocky planets orbiting one tiny star give us a system-level lesson. Compact strings of Earth-sized planets around red dwarfs may be common in our local universe, but while forming rocky worlds is easy, keeping their atmospheres under constant stellar radiation is the real bottleneck for making a truly habitable planet. So it's time to find out the truth beyond TRAPPIST-1. If this is the dense, extreme case at the edge of our 40 light-year bubble, what happens when we look at quieter red dwarfs with fewer, more widely spaced planets? Could some of those worlds actually be better bets for life than anything in this famous system? And how will we know which ones to trust? LH1140b, a super-Earth that might actually be friendly. To answer that, we need a nearby test case where the red dwarf is calmer, the planet is bigger, and the odds of keeping an atmosphere are actually in our favor. One of the best candidates does sit just beyond our 40 light-year line in strict terms, at about 41 light-years away, but it is too important to ignore. This is LH1140b, and in the hunt for alien life, it might be one of the most promising super-Earths we have. The planet orbits a small, cool red dwarf in the constellation Cetus. It should be noted that this world is not just slightly larger than Earth. With a radius about 1.7 times Earth's and several times the mass, surface gravity would be significantly higher. Walking here would feel heavy, but not crushing, and that extra gravity is crucial because it helps the planet hold on to any atmosphere it formed. Unlike the ultra-tight orbits in TRAPPIST-1, LHS 1140b circles its star in about 25 days, right in the middle of the Goldilocks zone. This means it receives a steady, moderate amount of energy, less intense than many red dwarf planets that hug their stars so closely they are blasted by radiation. The star itself seems relatively quiet, with fewer extreme flares than Proxima Centauri. Put together, that gives us a system where an atmosphere has a fighting chance. What do we know about the interior of this planet? From its mass and radius, astronomers infer a high density consistent with a mostly rocky composition. But the numbers also leave room for something more intriguing: a significant fraction of water, or volatiles. Picture a tidally locked world, one side always facing the star, the other an endless night, but with a deep global ocean or a thick, stable atmosphere that transports heat from day to night. Suddenly, instead of a scorched day side and frozen night side, you can imagine a broad twilight band with temperatures that are actually habitable. Here's where the James Webb Space Telescope enters the story as a pattern interrupt. We have talked about TRAPPIST-1, but JWST is now turning its mirrors toward L8's 1140b as well. By watching the planet pass in front of and behind its star, Webb can search for signs of an atmosphere, carbon dioxide, water vapor, and other greenhouse gases that would indicate a stable, temperate environment. So it's time to find out the truth about whether this super-Earth is merely rocky or truly Earth-like in climate. Optimistically speaking, LH1140b is a powerful counterpoint to Proxima b and the inner TRAPPIST-1 planets. Those smaller, more exposed worlds may have lost their heir to stellar tantrums, but while many red dwarf planets are harsh, this slightly larger super-Earth shows that not all are created equal, and some may be better at hanging on to the very atmospheres that make life possible. So, let's begin to widen our survey and see which other nearby worlds share this quiet, promising profile. GJ1214b, the cloudy sub-Neptune that broke our models, so if some red dwarf planets can hold on to thick atmospheres, what happens when a world has too much of a good thing? GJ1214b is one of the first nearby planets that forced us to confront that question. This world orbits a small red dwarf about 40 light-years away in Ophiuchus. It races around its star once every 1.6 days, at a distance so close that its year is shorter than a weekend. With a radius about 2.7 times that of Earth and several times Earth's mass, it falls into a strange middle ground. Not a rocky super-Earth, not a gas giant either. It sits in the sub-Neptune, or mini-Neptune, regime that does not exist in our own system. We know that Earth-like planets are fertile ground for life. After all, life arose here. But while we tend to focus on Earth-sized worlds in the Goldilocks zone, most of the planets we have actually found nearby look more like GJ1214b. This means, if we want to understand the real universe of planets, we have to understand these intermediate alien types. From its mass and radius, GJ1214b almost certainly has a thick envelope of hydrogen and helium, probably wrapped around a core rich and heavier materials. It should be noted that models allow for large amounts of water or other volatiles mixed in, perhaps forming a deep, hot ocean layer under a dense atmosphere. For years, astronomers hoped that by watching starlight filter through that atmosphere, we could read its chemistry like a barcode. But then, the data arrived. Hubble stared at GJ1214b through many transits. Instead of clear absorption features from water vapor, methane, or other molecules, the transmission spectrum was almost flat. No strong fingerprints, just a muted, featureless line. The best explanation? A high, opaque layer of clouds, or haze, blocking our view of the deeper atmosphere and erasing the signals we expected. In the hunt for alien life, this was a reminder that sometimes the universe simply draws the curtains, so it's time to find out the truth with a better tool. JEST has now watched GJ1214b not only during transits, but throughout its entire orbit, building a thermal phase curve. By tracking how the planet brightens and dims in infrared as different faces rotate into view, we can map how heat flows from the star-lit day side to the night side. The result? GJ1214b seems to redistribute heat efficiently, consistent with a thick, dynamic atmosphere, even if its clouds hide the details. Optimistically speaking, that makes it a rich laboratory for atmospheric physics, even though it is far too hot and puffy to be habitable. So, let's begin to see the pattern. Many of the planets within 40 light-years are not Earth-like at all, but by wrestling with cloudy sub-Neptunes like GJ1214b now, we are building the techniques we will need when a truly temperate, habitable world finally appears in our nearby census. And as we move on to other systems, we will see just how diverse those nearby neighbors really are. GJ367b and the ultra-short period extremes, so if many of our nearby planets are cloudy mini-Neptunes, what sits at the other extreme? There is a world so close to its star that the idea of an ordinary year almost stops making sense. Meet GJ367b. This tiny planet orbits a dim red dwarf, just about 31 light-years away, well inside our 40 light-year neighborhood. But while Earth takes 365 days to circle the Sun, GJ367b races around its star in roughly 8 hours. a full orbit in less than a workday. In the hunt for alien life, this is the sort of world we do not expect to be habitable at all, but it is scientifically irresistible. So, let's begin with its size and weight. GJ367b is only about 3/4 of Earth's radius, so at first glance, you might imagine a slightly smaller, maybe even Earth-like planet. But the mass tells a different story. When astronomers combined transit data with radial velocity measurements, they found it is far heavier than its size suggests. This means its density is enormous, higher even than Earth's, and much closer to what we see in Mercury. It should be noted that Mercury is already an outlier in our own system, with an iron core that dominates the whole planet. GJ367b looks like Mercury on steroids, a stripped, iron-rich core with only a thin rocky shell, if any. How do you peel away so much rock from a planet? Violent history. Intense early radiation from the star, brutal stellar winds, or giant impacts could all have removed lighter material, leaving behind this metallic remnant. Conditions on the surface would be extreme. At such a tight orbit, the planet is blasted with hundreds of times more energy than Earth receives. Models suggest temperatures well above 1000 degrees Celsius, hot enough to melt rock and create a lava world, perhaps with a glowing magma ocean on the dayside. There is no realistic atmosphere to speak of, no oceans of water, and no chance of a Goldilocks zone climate. Optimistically speaking, the only life here is the life of atoms in constant thermal chaos. So why do we care about such a hellish place? Because GJ367b is a perfect test case for our models of planetary interiors. Radial velocity tells us the mass, the transit depth tells us the radius, and together they pin down the density with exquisite precision. This means we can distinguish between rocky, iron-rich, and volatile-rich planets even when we will never see their surfaces directly. So it's time to find out the truth about our neighborhood. Worlds like GJ367b show one end of the spectrum, ultra-short period, scorched remnants. But as we move outward from these infernos, more temperate, longer period planets begin to appear, harder to find, yet far more interesting for life. Which of those quieter? Cooler worlds within 40 light-years might actually sit in the true Goldilocks zone, 55 Cancri, a packed system around a sun-like star. So, if the true Goldilocks worlds are harder to find, where do we look next? We have spent a lot of time with cool, faint red dwarfs, but what about planets around stars that feel a little more like home? So, let's begin with one of the most important. 55 Cancri. It sits just over our 40 light-year boundary, at about 41 light-years away in the constellation Cancer, but it is simply too iconic to skip when we talk about our nearby neighborhood. This is not a lonely star. 55 Cancri is actually a binary system, with a distant red dwarf companion, 55 Cancri b, slowly circling far away. The main attraction is 55 Cancri a, a bright, sun-like star hosting at least 5 confirmed planets. In the hunt for alien life, this is the kind of architecture we hoped to see. Those planets span an incredible range. Closest in is 55 Cancri a, an ultra-hot super-Earth so close to its star that a year lasts less than 18 hours. For a while, there was a dramatic idea maybe this planet was carbon-rich, with a mantle full of diamond. It sounded like science fiction, but while that captured headlines, new data painted a harsher, more realistic picture. This means 55 Cancri e is almost certainly a scorched, possibly lava-covered world, with dayside temperatures of thousands of degrees. Here is the pattern interrupt. Despite being so close that rock probably melts, 55 Cancri e might still have a dynamic atmosphere. Infrared observations hint at heat being redistributed from the dayside to the nightside, and possibly at clouds or vapor above oceans of magma. It should be noted that this is nothing like an Earth-like environment, yet it shows us that even small, rocky planets around sun-like stars can evolve into extreme, exotic states we never anticipated. Farther out, the system calms down. Additional planets occupy wider orbits, including 55 Cancri d, a Jupiter mass giant several astronomical units from the star. This outer giant, together with intermediate worlds between it and the star, makes 55 Cancri feel strangely familiar. Inner rocky or super-Earth planets, outer gas giant, complex gravitational choreography. Optimistically speaking, if moons or smaller, unseen planets exist in more temperate orbits, they could one day be interesting targets for habitability studies. However, none of the known planets in 55 Cancri sit squarely in the classical Goldilocks zone. Their orbits are either too close and hot or too distant and cold for liquid water on the surface as we understand it. So it's time to find out the truth about what this system really tells us. 55 Cancri is crucial, not because it hosts a clearly habitable planet, but because it demonstrates that complex, multi-planet systems around bright, sun-like stars already exist within our extended backyard. And that contrast matters. Our confirmed exoplanet sensor axis within 40 light-years is dominated by red dwarf systems, rich in tightly packed small planets. Sun-like stars, so far, contribute fewer confirmed and potentially habitable worlds. So where should we focus our next searches? On the common red dwarfs, or the rarer, more familiar stars like 55 Cancri A? In the next systems, we will see how that trade-off plays out, much closer to home. Tau Ceti, and the search for solar system cousins. So if red dwarfs dominate our nearby exoplanet map, where does that leave the stars that look more like our own sun? To answer that, we have to visit one of the great legends of both science fiction and Ceti, Tau Ceti. Tau Ceti sits just under 12 light-years away, glowing quietly in the constellation Cetus. It's slightly smaller and cooler than the Sun, but close enough that for decades it has been a favorite target for radio searches, for intelligent life, and a recurring home for fictional alien civilizations. In the hunt for alien life, a calm, long-lived, almost sun right next door is hard to ignore. But what actually orbits this star? That turns out to be surprisingly complicated. Radial velocity surveys, which look for the tiny wobble of a star as planets tug on it, have suggested a whole family of worlds around Tau Ceti, several super-Earths and mini-Neptunes, with orbital periods ranging from a few weeks to more than a year. Some of these candidates sit in or near the star's Goldilocks zone, where liquid water could, in principle, exist on a rocky surface. However, while this sounds like the ideal nearby solar system cousin, it should be noted that the evidence is right at the edge of what our instruments can reliably see. The signals are small, close to the noise level, and Tau Ceti itself is not perfectly quiet. Subtle changes in its surface, like star spots and magnetic cycles, can mimic the tug of a low-mass planet. This means different teams, working with different datasets and analysis methods, sometimes recover different lineups of planets. Are there 4, 5, more? Catalogs that only list fully confirmed worlds have to be cautious, and some of the Tau Ceti candidates end up in a gray zone, not disproven, but not secure enough to stand beside TRAPPIST-1 or Proxima Centauri b. So, why does a system wrapped in uncertainty matter so much? Because even a tentative picture of multiple small planets around a nearby sun-like star tells us something profound. It suggests that our own solar system is not an isolated fluke, that compact systems of super-Earths and mini-Neptunes might be common even around stars that look like the sun, not just around red dwarfs. Optimistically speaking, Tau Ceti is a preview of the kinds of architectures we will resolve clearly with the next generation of instruments. So it's time to find out the truth. As ultra-stable spectrographs and future space telescopes refine these wobbles and, eventually, try to see these worlds directly, one question hangs over Tau Ceti and its cousins. When we finally pin down a clean, confirmed, Earth-sized planet in the habitable zone of a nearby sun-like star, how will that change our view of Earth's place in the universe compared to all those red dwarf planets we have been cataloging so far? In the next section, we will look at how upcoming missions are designed to answer exactly that. Other nearby multi-planet red dwarfs, GJ 1061, Teegarden star, and more so if sun-like stars are only part of the story. What happens when we turn fully to their smaller, cooler cousins? In the hunt for alien life, we cannot ignore the quiet majority, the red dwarfs that fill our local volume of space. So, let's begin just 12 light-years away, with a faint star in horologium called GJ 1061. On a telescope image, it looks utterly unremarkable, but hidden in its subtle wobble are at least 3 planets, all discovered by radial velocity. Instead of watching them transit, astronomers measured the star's tiny back-and-forth motion as each planet tugged on it in orbit. This means we know their minimum masses and orbital periods, but not their exact sizes. 2 of these worlds, GJ 1061c and d, cluster near the inner edge of the star's Goldilocks zone. They likely receive similar or slightly higher energy than Earth, but from a very dim red dwarf whose total light output is only a fraction of the Sun's. Are they scorched desert planets, or compact ocean worlds with thick atmospheres redistributing heat across a tidally locked surface? It should be noted that without a transit, we do not yet have a clean way to measure their radii, densities, or air. A similar story plays out just half a light-year farther, Teegarden's star, roughly 12.5 light-years away. This ultra-cool red dwarf is so faint that it was only identified as a nearby star in 2003, yet it hosts at least 2 Earth-mass planets, Teegarden B and C. Both were also revealed by radial velocity, and both sit in or near the habitable zone, with temperate levels of starlight that, on paper, look remarkably friendly to liquid water. Their minimum masses are strikingly close to Earth's, making them some of the most enticing Earth-like candidates in our 40 light-year census. But again, there is a catch. Because these planets do not cross the face of their star from our viewpoint, we lack direct measurements of their radii and atmospheres. Are they rocky, water-rich, or wrapped in thick hydrogen envelopes that erase any chance for familiar life? So it's time to find out the truth, but our current instruments are stretched to their limits. Optimistically speaking, GJ 1061, Teegarden's star, and a growing list of similar systems are quietly rewriting our expectations. They may not be as famous as TRAPPIST-1 or Proxima Centauri, yet they add multiple potentially temperate, Earth-mass planets to our immediate neighborhood, all around very dim stars that were once considered unpromising. The emerging pattern is hard to ignore. Within 40 light-years, space is sprinkled with small worlds in or near the habitable zones of red dwarfs. But we are missing exactly what matters most. We need to see their skies. We need to know if any of these planets actually carry atmospheres, clouds, or biosignature gases. In the next section, we will look at the future telescopes designed to do exactly that, and ask a deeper question. When those first spectra arrive, what if the closest truly living world does not look like Earth at all? Single planet neighbors, lonely worlds around quiet stars, but what if those first spectra do not just reveal strange atmospheres? What if they also expose something else we have been missing? Entire hidden planetary families around stars we currently think of as having only one world. In the hunt for alien life, we often focus on the crowded celebrity systems like TRAPPIST-1, yet, scattered through our 40 light-year neighborhood are quieter, lonelier entries in the catalog. These are stars with a single confirmed planet on the books, at least for now, and some of them are surprisingly close. Take Barnard's star, just under 6 light-years away. It is an old, fast-moving red dwarf, at least twice the age of the Sun, sliding across our sky like a silent ember. Orbiting it, we think, is Barnard's star B, a cold super-Earth at roughly 3 times Earth's mass, circling every 233 days at a distance where sunlight is feeble. This means its surface is probably far below freezing, more like a dimly lit Kuiper Belt object than a classic Goldilocks world. But while Barnard's star B is likely too cold for surface oceans, the system itself is fascinating. An ancient, stable star with a long, quiet history could give any subsurface oceans or deep atmospheres a lot of time to evolve. It should be noted that some astronomers still debate the signal, but if this planet is real, it may be one of the oldest nearby super-Earths we know. Now, contrast that with Ross 128, about 11 light-years away. This red dwarf is unusually calm, flaring far less than Proxima Centauri. Its known planet, Ross 128b, is roughly Earth mass and orbits in a tight, temperate zone where the estimated stellar energy is close to what Earth receives. The planet does not transit, so we cannot use the usual backlit method to probe its atmosphere. So it's time to find out the truth in a different way. Ross 128b has become a prime target for future direct imaging missions, which will try to separate the faint light of the planet from the star itself. If we can do that, we might finally read its atmosphere for signs of clouds, greenhouse gases, or even biosignatures. Optimistically speaking, this could be one of the first nearby non-transiting planets where we truly test whether an Earth-like world around a quiet red dwarf can be habitable. Here's the pattern interrupt. When we label these as single-planet systems, we are almost certainly misleading ourselves. The universe is not obliged to stop at one. Detection methods favor the biggest, closest in, or most massive worlds first. Smaller companions, or planets in wider orbits, can easily hide in the noise. This means Barnard's star, Ross 128, and other neighbors like Wolf 1061 or GJ 15a may well host additional planets that our current data are simply not sensitive enough to reveal. So, let's begin to think of our 40 light-year census as a living document, not a finished map. As radial velocity measurements accumulate and new direct imaging telescopes come online, many of today's lonely stars could suddenly light up with second, third, or fourth worlds. And in the next section, we will ask a deeper question. When those hidden companions finally emerge, will the most promising home for life be the first planet we found, or the ones that were invisible all along? What we actually know, sizes, orbits, and densities explain so. When all these new worlds finally come out of hiding, what do we actually know about them? Most of the time, it comes down to just 3 numbers. The first is the orbital period, how long a planet takes to go around its star, from a repeating dip in starlight during a transit, or a rhythmic wobble in radial velocity data. We can time those orbits with astonishing precision. A year on TRAPPIST-1, just over 6 Earth days. Proxima b, about 11. This means we immediately know how much energy they receive and whether they sit inside, outside, or skimming the edge of the Goldilocks zone. The second key quantity is radius. Only transiting planets give us this. When a world crosses the face of its star, the tiny fraction of light it blocks reveals its size. TRAPPIST-1's 7 planets are a perfect example, all close to Earth-sized because each transit tells us exactly how big they are compared to their ultra-cool red dwarf. The third is mass, usually from radial velocity or, in tightly packed systems, from transit timing variations. The star's wobble tells us how strongly a planet's gravity pulls on it. Combine that with the radius, and suddenly we have density. And density is where these worlds stop being just dots in a catalog and become real places. In the hunt for alien life, density is our first crude X-ray of a planet's interior. TRAPPIST-1's worlds, for instance, cluster around rocky, Earth-like densities that strongly hints at iron cores and silicate mantles, not puffy gas envelopes. GJ367b, on the other hand, is so dense it seems almost overbuilt, pointing to an iron-rich composition more like a stripped planetary core than a gentle Earth twin. At the opposite extreme, GJ1214b's low density tells a different story. A mini Neptune with a thick volatile envelope, perhaps loaded with water and hydrogen, wrapped in an atmosphere G-West now sees as heavily clouded. It should be noted that this density magic only works when we have both mass and radius. For non-transiting planets like Proxima b or Ross 128b, radial velocity gives us a minimum mass and an orbital period, but no direct size, no true density, and no firm composition. Are they compact, iron-heavy worlds, or slightly larger, water-rich planets? Until we can directly image them, we are guessing within broad limits. So let's begin preparing for the next layer of complexity, atmospheres. If mass, radius, and orbit sketch the outline, then the atmosphere paints in climate, surface conditions, and any realistic chance for life. Optimistically speaking, density can tell us where a rocky, potentially habitable surface might exist, but whether that surface is a frozen desert, a steaming greenhouse, or a truly Earth-like oasis. So it's time to find out the truth in the next section, where we follow the first fragile hints of alien skies, atmospheres, or bare rock. JWST, Hubble, and ground telescopes weigh in, so if density only sketches the outline, how do we actually read the weather report on an alien world? How do we know whether we're looking at a living sky or bare rock baked in starlight? In the hunt for alien life, the key trick is to use the star itself as a backlight. When a planet passes in front of its star, a tiny fraction of that starlight filters through any atmosphere before it reaches us. Different molecules absorb different colors, so the spectrum of the star changes by a minuscule amount. This means water vapor, methane, carbon dioxide, even hazes and clouds can leave their fingerprints as the planet transits. This is called transit spectroscopy, and it has transformed our nearby neighborhood from a list of orbits into a catalog of possible climates. Hubble and large ground-based telescopes pioneered the method on big, puffy worlds, proving we could see sodium, water, and clouds light years away. It should be noted that these early targets were mostly hot Jupiters and mini Neptunes, not small, cool, Earth-like planets. But while the first successes were on giant worlds, the same physics applies to the compact systems within 40 light-years that we care about most. Take GJ1214b, about 48 light-years, but so influential we have to mention it. Its spectrum, from Hubble and now JWST, is almost completely flat. No sharp waterlines, no obvious methane features. The best explanation? A deep high cloud or haze deck that hides whatever atmosphere lies below. That cloudy, featureless spectrum was our warning. Small planets can be maddeningly secretive. So, let's begin to look at the truly nearby systems. GWST has now turned this same technique on the TRAPPIST-1 planets. For the inner worlds, especially TRAPPIST-1b and 1c, the absence of strong spectral features tells us they lack thick, hydrogen-rich envelopes. Combined with other data, we see hints that they may have only very thin atmospheres, or almost none at all. Hardly the lush, habitable environments we once imagined. Transit spectroscopy is only half the story though. We can also watch how a planet glows in infrared as it orbits its star. When the planet slips behind the star, its own thermal emission briefly disappears. By measuring that tiny dip and tracking the infrared brightness through the whole orbit, JWST and ground telescopes can build a thermal phase curve, a map of day-night heat distribution that reveals how efficiently an atmosphere moves energy around. For TRAPPIST-1b, that thermal curve suggests a scorching dayside with little heat transported to the night, again pointing to a bare or nearly bare rock. For slightly larger, cooler worlds like LHS-1140b, ongoing campaigns are trying to detect both spectral features and phase curves, searching for signs of a thick, protective atmosphere over what might be a temperate ocean planet. Optimistically speaking, G-West's sensitivity is finally reaching down to the regime of small, cool planets in the Goldilocks zone within our 40 light-year bubble. We are right at the threshold where we can simply ask, is there an atmosphere at all? So it's time to find out the truth in the next section, where we confront the first decisive yes or no answers for the most promising nearby worlds, and what those answers mean for real habitability, tidal locking, eternal day, and the new habitable zone. So if we can finally ask whether these nearby worlds have atmospheres, we also have to ask something stranger. What does day and night even mean on most of them? Because for the majority of potentially habitable planets within 40 light years, a day never ends. Tidal locking sounds exotic, but the idea is simple. When a planet orbits very close to a small red dwarf star, gravity stretches it slightly and acts like a cosmic brake. Over millions of years, the rotation slows until the planet always shows the same face to its star. One hemisphere is locked in eternal daylight, the other is trapped in permanent night. Think of the moon always turning the same face toward Earth. Now imagine Earth itself doing that to the sun. Early on, this looked like a disaster for life. Astronomers assumed the day side of a tidally locked planet would roast, while the night side would be so cold that the atmosphere would literally freeze out onto the surface. No air, no liquid water, no chance of an Earth-like climate. In the hunt for alien life, these red dwarf systems were often written off as beautiful but dead. But while that picture was simple, the real physics turns out to be far more interesting. As climate models improved, researchers started to ask a new question. What if the planet has even a modest atmosphere, or an ocean? Could winds and currents move heat from day to night? The answer from the simulations was a clear yes. This means that instead of a world split between furnace and freezer, you can get a broad, stable twilight ring around the planet, the terminator, the boundary between day and night. In that band, temperatures can sit in the liquid water range, even while the substellar point bakes, and the far side stays dark. TRAPPIST-1 is one of the best examples. It orbits deep inside the Goldilocks zone of its cool red dwarf, almost certainly tidally locked, with one hemisphere forever staring at the star. Yet models show that with an atmosphere just a bit thicker than Earth's, winds could circulate heat efficiently, creating a wide, habitable twilight belt. LH1140b, a denser super-Earth around another nearby red dwarf, may do something similar, perhaps with the Terminator Ocean under a thick, protective atmosphere. Optimistically speaking, these planets are not failures of habitability, they are new climate regimes. Here is the pattern interrupt. If we cling to the classical idea that only fast-spinning, sun-like worlds count as habitable, then almost every promising planet in our 40 light-year census fails. It should be noted that most of our nearby candidates orbit dim red dwarfs, close in, and are probably tidally locked. So it's time to find out the truth about what Earth-like really means. In the next section, we will follow the starlight itself as it filters through these alien atmospheres, and see whether any of these eternal day worlds actually show the fingerprints of air, clouds, and maybe even oceans, ranking our neighborhood from lava worlds to maybe habitable. So if most of our nearby Earth-like planets are actually eternal day, red dwarf worlds, how do we make sense of them all? In the hunt for alien life, we need some way to rank this crowded little neighborhood, even if our information is still frustratingly incomplete. So, let's begin with a simple, honest scheme. Think of three broad tiers. First, the clearly uninhabitable, worlds that are either oceans of magma or giant balls of gas, with no solid surface for life as we know it. Second, the marginal cases, planets that are probably too hot or too cold, but still interesting laboratories for climate physics. Third, the maybe habitable class, temperate, likely rocky planets in or near the Goldilocks zone, where a decent atmosphere could, in principle, support liquid water. This means we can start dropping specific planets into these boxes. In the lava world category, GJ367b is an easy call. It orbits its star in just about 8 hours, so close that its dayside temperature likely exceeds 1500 degrees Celsius. Any original atmosphere has almost certainly been blasted away, leaving an exposed, iron-rich core. 55 Cancri E, only a bit farther than our 40 light-year cutoff, is another extreme example, probably a tidally locked, superheated world with molten rock seas under a thick, high-pressure atmosphere. Spectacular? Yes, habitable? habitable? No. On the opposite side, we have the frozen marginal planets. Barnard star B, for instance, orbits well outside the classic Goldilocks zone of its cool red dwarf. Even with a generous greenhouse atmosphere, climate models suggest a mostly frozen surface, perhaps with pockets of warmth underground. It should be noted that such a world might still be geologically active and could host subsurface reservoirs, but surface life would face an almost impossible struggle. Then, we arrive at the maybe tier, where things become far more interesting. TRAPPIST-1e sits right in the middle of its system's habitable zone, with a size and mass close to Earth-like values. LH-1140b, slightly larger and denser, may be a rocky super-Earth receiving a comfortable amount of starlight. Teegarden star B and C both orbit near the inner and outer edges of that star's Goldilocks zone. Ross 128b receives a bit more light than Earth, but circles a relatively quiet red dwarf, making it a prime target. Optimistically speaking, these are the places where atmospheres, clouds, and maybe oceans could exist, but while they are our best candidates, they still sit firmly in the maybe box. We do not yet know whether any of them actually hold on to thick, life-friendly atmospheres. Stellar activity billions of years ago may have stripped them bare. Even when we measure mass and radius well, composition degeneracies mean we cannot be sure how much water or iron they hide. So it's time to find out the truth with better data. Think of this ranking as a snapshot, not a final verdict. A rough map of our options within 40 light years. If you could choose only one of these planets to visit or study first, which would it be? In the next section, we will follow that instinct and ask what the next generation of telescopes must do to turn these maybes into real answers about life. What our nearby census says about Earth's uniqueness, so if that ranking was just a snapshot, what does the bigger picture actually look like? And what does our little 40 light year neighborhood really say about how special Earth is? Or is not. In the universe, when we zoom out and look at every confirmed planet within this bubble, a striking pattern jumps out from the data. Red dwarf stars absolutely dominate. TRAPPIST-1, Proxima Centauri, LHS 1140, GJ 1214, GJ 367, and many more are all small, cool stars with tight, compact systems. Their planets huddle close in, whipping around in days, not years, often locked with one face permanently staring at the star. This means our nearby census is filled with worlds that are super-Earths and sub-Neptunes, not neat rows of Earth clones. Compare that to our own solar system. We have relatively wide orbits, no super-Earths at all, and a single small rocky world sitting comfortably in the Goldilocks zone. But while we once assumed that this layout was a kind of cosmic standard template, the systems around us tell a different story. Many nearby stars cram multiple planets inside the orbit of Mercury. Some, like GJ 1214b, seem to wear thick, volatile envelopes, perhaps steam-rich or cloud-choked. Others may be stripped cores or lava worlds. So it's time to find out the truth about our typical status. We might actually be the weird ones. In the hunt for alien life, that weirdness cuts both ways. On one hand, small rocky planets are clearly common. TRAPPIST-1 alone offers 7 Earth-sized examples, and Proxima Centauri B and L8's 1140b show that temperate orbits do exist around red dwarfs. Optimistically speaking, that means nature likes to build solid surfaces where atmospheres and oceans could, in principle, form. On the other hand, a truly Earth-like combination, a stable, middle-aged, sun-like star, a long-lived temperate climate, and no giant planet crowding the inner system, looks rarer in our immediate neighborhood. It should be noted that this apparent scarcity might say as much about our tools as about the universe itself. Our instruments are exquisitely tuned to find planets that transit small red dwarf stars or tug on them with strong gravitational signals. Spotting an exact Earth twin around a sun-like star at a 1-year orbit is dramatically harder, especially within such a small volume of space. So when we see few nearby Earth analogs around sun-like stars, we have to ask, are they truly rare, or just hiding below our current detection limits? So, let's begin to treat this 40 light-year census as a reality check rather than a verdict. It does not settle the rare Earth debate, but it loudly tells us that planetary systems are more inventive, more chaotic, and more diverse than the tidy model we grew up with. The real question now is, what kind of telescope do we need to finally catch an undisguised Earth twin in the act of being habitable? The next wave, Habitable Worlds Observatory, and future missions to answer that question, we have to admit something slightly uncomfortable. Right now, we do not actually have the telescope we truly need. In the hunt for alien life, Everything we have used so far has been clever workarounds. We have been reading shadows and wobbles, not faces. NASA's answer to this problem has a very direct name, the Habitable Worlds Observatory. This is not just another space telescope, it is a concept specifically built to do one thing we have never done before: directly image Earth-sized planets around Sun like stars, and then dissect their atmospheres for signs of life. Imagine a mirror, larger than Hubble's, operating in visible and ultraviolet light, armed with an ultra-precise coronagraph that can blot out a star's glare by a factor of billions. This means that, for the first time, a pale blue dot around a nearby star would not be a metaphor. It would be a literal, resolved object in our data, but while Habitable Worlds Observatory is the headline act, it should be noted that it is not alone. On the ground, extremely large telescopes with mirrors 30 to 40 meters across are rising in Chile and elsewhere. These ELTs, using adaptive optics and advanced coronagraphs, will try to tease out the faint reflected light from planets around nearby stars within our 40 light-year bubble. In space, designs inspired by LUVOIR and other large aperture concepts are feeding directly into the Habitable Worlds plans, keeping the door open for even more ambitious missions. Optimistically speaking, a future formation, Flying Starshade, could join the party, drifting tens of thousands of kilometers from a telescope to carve out an artificial eclipse. Why does this matter for worlds like Proxima b or Ross 128b? Transit and radial velocity methods tell us mass, radius, and orbit. They hint at whether a planet is rocky and roughly how much starlight it receives. Direct imaging adds something qualitatively different. It lets us measure the planet's own reflected light, separate from the star, and spread that light into a spectrum. In that spectrum, we can search for oxygen paired with methane, water vapor with carbon dioxide, chemical combinations that are very hard to maintain without active biology reshaping the atmosphere. So it's time to find out the truth about these nearby systems with tools that can finally see them as worlds, not just numbers. There is a catch. These are decades-long projects. The Habitable Worlds Observatory is being designed now, but it will likely launch in the 2040s. The ELTs will spend years perfecting their techniques. That means the planets we have met in this video are not just a catalog, they are the first detailed case studies for an entire generation of astronomers. If the first unambiguous sign of life beyond Earth comes from a nearby planet, it will almost certainly be on one of the worlds we have just toured, or on a quiet, yet undiscovered neighbor, hiding within the same 40 light-year Goldilocks bubble around us. And that raises one final question. What happens when that first spectrum comes back and it does not look lifeless at all? Recap: every confirmed exoplanet within 40 light-years in one mental map, so if that first spectrum hints at life, where in this nearby crowd of worlds is it most likely to come from? To answer that, we need one last flyover, a single mental map that pulls our entire 40 light-year neighborhood into focus. So, let's begin at the place we started, Proxima Centauri and Alpha Centauri, just over 4 light-years away. Proxima b clings to the Goldilocks zone of a temperamental red dwarf, blasted by flares, yet still one of the closest potentially habitable planets we know. A little farther out, the brighter Alpha Centauri pair may host more subtle companions, but for now, Proxima is the clear headline act of that system. From there, we swept outward through the red dwarf heartland, compact, multi-planet systems like TRAPPIST-1, LH1140, and GJ1214. These are the workhorses of our tour. TRAPPIST-1 alone gives us 7 Earth-sized planets packed tighter than the inner solar system, 3 of them inner near the habitable zone. LH1140 offers a dense, cool super-Earth in the temperate region. GJ1214b, with its thick, high-altitude haze, may be an extreme water-rich world. In the hunt for alien life, these are the planets we keep coming back to. Only after that did we turn to the rarer sun-like systems. 55 Cancri with its hot lava world, and outer giant, Tau Ceti, with its quieter, more solar-style architecture, plus a scattering of other G and K-type stars hosting super-Earths and mini-Neptunes. But while these feel familiar, because their stars resemble our own, their planets are often not Earth-like at all. This means our own solar system may be the oddball, not the template. If we step back, what does the census look like? Within roughly 40 light-years, we now have several dozen confirmed exoplanets. Most of them orbit red dwarfs. Most are not small, blue Earth twins, but a mix of scorched lava planets, puffy sub-Neptunes, and hefty super-Earths, with only a handful sitting in temperate orbits where liquid water is plausible. The main scientific lessons are surprisingly clear. Red dwarfs dominate our nearby sample, so understanding their flares, magnetic fields, and atmospheres is essential. It should be noted that atmospheres on the planets themselves remain the crucial unknown. JWST has only just begun to peel back those layers. Tidal locking, once seen as a death sentence, now looks survivable if a planet has air or oceans to move heat around, and the most Earth-like conditions around Sun-like stars at Earth-like orbits are still the hardest to probe, but they are finally within reach of upcoming missions. Optimistically speaking, this map is not finished. New planets will be added. Some candidates will quietly disappear. Some stars we thought had a single world will blossom into rich planetary families as more data arrive. So, hold this 40 light-year bubble in your mind, not as a static list, but as a living atlas of worlds. Because in 10 or 20 years, when we redraw this map, how different will it look? And what new kinds of life will it allow us to even imagine? Your turn. Which nearby world would you visit first? So, with this living atlas in mind, let's turn the telescope around for a moment. If you could choose just one of these nearby planets to visit or to study up close, which world would it be? In the hunt for alien life, that choice says a lot about what each of us finds truly interesting. Do you go straight for Proxima b, simply because it is the closest, only 4.24 light-years away, hugging a volatile red dwarf that might strip its atmosphere? Or do you skip the nearest option and head for a more balanced target, like TRAPPIST-1, sitting right in the middle of its star's Goldilocks zone, with JWST already telling us it is not wrapped in a thick Venus-like shroud? Maybe you are drawn to LHS 1140b, a heavier super-Earth where surface gravity would press you into the ground, but where some data hint at a dense atmosphere, and perhaps even an ocean. It should be noted that this planet might be one of our best chances to study a potentially habitable world that is not quite Earth-like, but still tempered enough for liquid water. Or perhaps Teegarden's star sea calls to you, a compact world in a tightly packed system, orbiting a cool star only 12 light-years away. Would you stand in its permanent twilight, on the line between scorching day and frozen night, and watch its dim sun hang fixed in the sky? How much does the drama of that tidally locked boundary matter to your choice? Then there is Ross 128b, circling a relatively quiet red dwarf, where fewer flares might mean a better chance for a long-lived atmosphere and stable climates. And at the opposite extreme, we have 55 Cancri, a lava world racing around its star in less than a day, with a surface that may literally glow. Do you choose the place that could host life, or the place that would simply take your breath away with its landscapes? So, let's begin your personal ranking. In the comments, tell us which of these planets you would pick first, and why. Are you prioritizing scientific payoff, raw visual spectacle, the odds of finding biology, or the sheer engineering challenge of surviving there? Now, a thought experiment. So it's time to find out the truth about your preferences. If tomorrow JWST, or a future habitable worlds observatory, found a clear biosignature, oxygen and methane in disequilibrium, on one of these worlds, would your answer change? This means we would know that somewhere in that distant atmosphere, chemistry is being pushed out of balance by life. Optimistically speaking, humanity's next steps would shift overnight. New missions designed around that single star system, new telescopes built just to read that alien sky in more detail. When you make your choice, imagine that future as well. Because these are not just entries in a catalog, they are real worlds, with real skies and real histories, waiting for us to decide which story to follow first. Closing CTA. Join the ongoing hunt in our 40 light-year neighborhood, so where does that leave us? Standing at the edge of this 40 light-year map we have just walked through together. It should be noted that the story we have told tonight is not finished. Every confirmed exoplanet in this neighborhood is a snapshot, not an ending. New data from JWST, from sharp-eyed ground-based telescopes, and from future missions will redraw this picture again and again. Atmospheres we can only guess at today may be measured in detail tomorrow. Maybe habitable can quietly, suddenly, become very likely not. Or, just possibly, this looks strangely Earth-like. In the hunt for alien life, that is the real excitement. TRAPPIST-1, Proxima Centauri, L8 1140, GJ 14, 55 Cancri, Tau Ceti. These are not just names, they are active investigations. As JWST stares through the thin light of each transit, as instruments track tiny dips and subtle colors, the atmospheres of these planets will either reveal themselves or slip away into mystery. This means the census of every confirmed exoplanet within 40 light-years will change. Worlds will be added. Some may be reclassified classified. A few might move from the interesting column into the priority target for life column almost overnight. So, let's begin a longer journey together. If you want to see what happens next to TRAPPIST-1, to Proxima Centauri b under its flaring red dwarf sky, to LH1140b and the cloud-wrapped GJ1214b, make sure you subscribe to the channel and turn on notifications. Do you want to be there the day we can finally say whether TRAPPIST-1 has an atmosphere or whether LH1140b hides an ocean? Then stay with us, because we will follow these systems as the data arrives. Share this tour with anyone who loves space, science fiction, or those big, unsettling questions about life in the universe. For them, this is not just a list of planets, it is a guided tour of our real cosmic neighborhood, a place where lava worlds, steam-shrouded mini-Neptunes, and genuinely habitable candidates all orbit side by side. Who in your life would enjoy standing on an imaginary shoreline on TRAPPIST-1, or under the dim red glow of Proxima, and asking, could anything live here? If you want to explore further, check the description. You will find links to interactive exoplanet catalogs and visualizers that let you fly through this 40 light-year region yourself. You can watch new worlds appear as they are confirmed, compare orbits, test different atmospheres, and see how our neighborhood evolves year by year. Optimistically speaking, you might even bookmark a favorite planet and follow its story as the measurements improve. So it's time to find out the truth, not just from a single video, but from a long, careful watch. Somewhere within 40 light-years, there may already be a living world looking back at the same stars we see. We do not know which system it orbits, we do not know what its sky looks like, but while the universe keeps its secrets for now, our job is clear. Together, we keep watching, we keep refining this map, and we keep asking the question until one of these nearby planets finally answers it.